Welcome to our discussion on bending moment and shear force diagrams. I would like to continue with our discussion on strength of material. Specifically now, we are on bending moments and shear forces. We wanted to see on how the diagrams look like. So we'll use the different examples on how to undergo the preparation for these diagrams. So we are given this: determine the expressions for the bending moment and shearing force distributions for the following simply supported beam, and plot the bending moment and shearing force. We have got, this is the simply supported beam being supported at A and B, and with the load being at C of 3 kilonewton. So let's see on how. First of all, we need to calculate the reactions, that is the force that is at R1 or RA and R2. Here one can say RA or R1, here R2 or RB. So calculating for reactions or resolving vertically, the forces that are acting vertically is the summation of R1 plus R2 or RA plus RB should be equal to the forces acting downwards. That is following the second principle of moment. That is, the sum of forces acting downwards must be equal to the sum of forces acting upwards. So this, as a beam is symmetrically loaded at the center, so R1 is equal to R2. How? Because R1 is equal to R2, that means we have to divide the 3 kilonewton, which is acting downwards, so they share equally. Because they are equally placed, so they will share the load acting downwards. That's why R1 and R2 each is equal to 1.5 kilonewton. So for the bending moment expressions, we have to regard the range from A to C, and in between we have an imaginary line that is X cutting this section. There we'll have the bending moment expression, that is R1 times X, the distance of X being at X. R1 times X is equal to 1.5. 1.5 is our load, and X is the distance from R1 or RA. So such kind of expression gives a straight line. So from point A, or from reaction 1, we'll have to go up to 1, or to go the distance of X. So let's go check for the range of CB. CB in between, there is X. So the moment there, we have to start with the bending moment, that is R1 times X. You have to subtract the part 2, the range of CB, which should be the total, which is 3, but the distance should be X minus 1. So the expression becomes 1.5x minus 3x plus 3. So putting the like terms together here gives the expression that is 1.5x plus 3 also gives the straight line. Let's go see for the shearing forces. Shearing force expressions at the range of AC. So the shearing force is equal to 1.5 kilonewton. Here, the reaction. We are taking the reaction which is going positively, that means upwards, from point A, or reaction 1 is the direction is upwards. So the range of CB, the shearing force there, we have to take the one that was going upwards, subtracting with the total force, which is 3, you get the minus 1.5 kilonewton. This means that the direction from it is downwards, so it's indicated by a negative sign. Let's see how now the diagrams, how they look like. For the bending moment, from reaction A, the range of A to C, it was raised up to 1.5. Then it had to return, that is a negative now, to the CB. That's why there was a negative sign going downwards. This was raising up, this was going down. For the shearing force diagram, from 0, origin here, equilibrium position. So the reaction here is reaction 1 or reaction at A is raised to 1.5. Then it has to go down at the center. Mind you, it was 3 here. Going downwards, this total amount is 3, but from origin here is 1.5 downwards. The mark, if it was the number line, you could see this is negative 1.5 because it is beyond the origin. That's how we say the expression here is a straight line, also here is a straight line. Also, from A to C is a straight line. There's a diagram for the bending moment of a simply supported beam and a load being at the center. Let's see another example for the beam, simply supported beam again, but this is not at the center. So we have to calculate again the reaction at A and the reaction at B. However, this case, the force that is acting downwards is not located at the center. As you can see, the total length of the beam is 3 meters, but from A is 2 meters, and from B is 1 meter. Taking moments about B, if we take moment from B, our B is somewhere there, reaction at B. So if we take moment there, it is R1 times 3, total length, that is the reaction at A, that is clockwise, and the anti-clockwise will be 4 times 1. We are at B, so the distance is 1 times 4. It is going anti-clockwise, but this one reaction is going clockwise, this direction. So the distance is taken from B, which is 1 plus 2 becomes 3. So because this one goes this direction, so so we have to equate the two equations, expression, that is 3 times R1 or RA should be equal to the anticlockwise, because this one is going to the anticlockwise if we are standing here being at B. So it is 4 times 1. We have to equate the two expression. That's why it is 4 times 1, R1 times 3, hence. So making R1 the subject in our expression, we get R1 is equal to 1.33 kilonewton. So resolving vertically, as we have done for the first case, the second principle of moment, which regards that the sum of the forces acting downwards must be equal to the forces which are acting upwards. So the R1 and the R2, they are acting upwards, and 4 is acting downwards. So R2 can be determined by 4 minus R1. R1, mind you, is 1.33. So 4 minus 1.33, it comes 2.667. So R2 is 2.667, and R1 is 1.33. At the working for the bending moment expression, the range, that means from A to C, in between there is X line. So being at X, the bending moment can be regarded as the reaction or the force, which is R1 or RA times the distance X. So the moment there becomes 1.33x. And of course, it's a straight line again. When you go for the range of CB, and from X, it is reaction 1 or reaction at A times X. We have to subtract 4 bracket X, the total distance, minus 2, the distance to the left, from C, then bracket, it becomes 1.33x minus 4x plus 8. Putting the like terms together, the expression becomes 2.667x plus 8. It gives a straight line. Shearing force, how is the shearing force expression? The range of AC, we had AC, the reaction at RA or R1, positively moving upwards, it is 1.33 kilonewton, and the range of CB, mind you, we are searching for R2. R1 minus 4, and the R1 is known, is 1.5, positive minus 4, it becomes negative 2.667 kilonewton. The sign negative indicates the direction, that is downwards, and positive, for our case, it means upwards. Let's see how they are drawn. So the range AC, the shearing, the bending moment indicates that it is 2.6 kilonewton meter, and for the shearing force at A, the positive is 1.33 kilonewton, and it has to turn back in direction here. The magnitude here, it indicates 1.33, the mark here, but just to go down to the magnitude of the total was how much? Was 4. So this plus this one, it becomes 4. So the mark down or beyond the origin or axis here, it is negative 2.6 kilonewton. That's how you can indicate, you can show the shearing force and the bending moment for our case. Example 3, determine the expressions for the bending moment and shearing force distribution for the following simply supported beam. Hence, plot the bending moment and the shearing force diagrams. Mind you, we are working on simply supported beam, but with the two loaded forces, with the two forces at C and D. And they are equally spaced, however, they have different loads. So first of all, you have to determine the reactions. You have to solve for reactions. So taking moments about B gives R1 times 3, R1 times 3, or R1 here is here, R1 times 3. The total distance is 3 here B. So 1 plus 1 plus 1, it becomes the distance, which is how much? It is 3 meters times R1, RA. If it is A, or you regard R1, so you get such kind of expression. So R1 times 3 should be equal to 1 times 2 plus 4 times 1. Where do we get this? It is here. So it is 4 times 1, or it is plus 2 is the distance, times 1, the load. How we get this expression. So R1 becomes, the total is 6 on the right hand side, divided by 3, making the R1 the subject to our expression. So we get 2 kilonewton. Reaction 1, or reaction at A, is 2 kilonewton. I have to go back for our second principle of moment, that is R1 plus R2 is equal to 1 plus 4, which is 5. And mind you, we have already determined the R1, so we know the R1 from the total, which is 5. Subtracting 2, you remain with 3, which is for R2. So for the bending moment expression, at the range of AC, it will be R1 times X, as usual. It gives a straight line, which is 2X. And CB, it is R1 times X minus the load, which is 1. In bracket, X minus 1, the distance. Bracket, the expression becomes 2X minus X plus 1. It gives a straight line for this case of CB. At the range of DB, we have to start with the R1 as well. R1 times X minus the load of 1 kilonewton. In the bracket, the distance total is X minus 1. Bracket minus 4, the load of 4 kilonewton. In the bracket, X total, we regard the total distance, minus 2. The distance to the left is now is 2. 1 plus 1 is 2. 2 meters. So you have to subtract. Then you get the expression 2x minus x plus 1 minus 4x plus 8. It gives bending moment is negative 3x plus 9, which is a straight line. So let's see for the shearing forces. taking the range of AC, so the shearing force will be R1, which is 2 kilonewton. The range of CD, or at CD, it is R1 minus 1, R1 minus 1. R1 minus 1 is, R1 is 2. So 2 minus 1, it becomes 1. And the range dB is R1 minus 1 minus 4. The two are going downwards, mind you. They are in the opposite direction. So R1 minus 1 minus 4, it becomes, R1 is for 2. 2 minus 1 minus 4, it gives negative 3 kilonewton. Remember that the negative is for direction, so it is 3 to the opposite direction. How is it drawn? So starting with the bending moment, first case, it is a range of AC, it is 2 kilonewton meters, as it has been raised. Also, up to the 3 kilonewton, it has to go downwards. There was an increment of 1 kilonewton in a first case. Yeah. We started with the expression, the bending moment, that is 2x, then followed by x plus 1. You remember we said what is x for this range of CB? It should be x plus 1. For the case of range of CB, range of AC is 2x. 2x. Range of CB is x plus 1. Range of DB is 3x plus D. So you can see now, range of AC, how does it look like? And there at dB, we had negative, that means it was going to the origin, changing the direction. Example 4. Determine the expression for the bending moment and the shearing force distributions for the following simply supported beam. Yet we are dealing with the simply supported beam, but the only difference here is the position for the load. Position for the load. Total length is 6 meters. So we have got A, B, C, D. Start, how to go, have to take moment. Taking moments here, we have to stand at D. This will give us R1 times 2 plus 4. This 4 should be multiplied by 0. 0 is for the distance, is no distance because we are at the load 4. Four times 0 because we are at D. So there is no distance to reach this 4 kilonewton. We are standing at D. So the force, the force is 4 kilonewton, but the distance is not there because we have not moved. We are at D. So take a moment with regard to this force 4, the moment will be 0. Let's continue. See. So it is R1 times 2, and it should be equal to 1 times 4. 1 times 4 4 is for the distance. 4 is, mind you, this one, R1 times 2 is going to the, it is for the right clockwise direction. Clockwise moment is like the movement of a watch. If we are standing here, so if this beam is moving this direction, so the distance is 2 meters multiplied by RA, R1 should be equated to the force that is opposing being here. So if it's pushing downwards, this force, which is 1 kilonewton, which is going anti-clockwise, so the distance is 4 because we have to add up 2 meters plus 2 becomes 4. So 4 times 1 kilonewton so here, hence R1 is equal to 2 kilonewton. Because here we have, it is R1 times 2, it becomes 2 R1, there is 4. So making R1 the subject in our expression, it becomes 2 kilonewton. Using the second principle of moment, that is R1 plus R2 is equal to 5. So you can determine now the value for R2, which is 3 kilonewton. Working for the bending moment expression, range CA at X, it is minus 1x, and this one, it is negative x, and this one will be a straight line. Range of AB at X, R1 is negative 1. So R1 times X minus R1 in bracket X minus 2, it becomes negative 1x plus 2x minus 4. Putting the like terms together, you simply get the expression x minus 4, which is a straight line. Range of dB at x bending moment is equal to minus 1x minus R1 in bracket x minus 2 is equal to minus R2 in bracket x minus 4 minus 4 in bracket x minus 4 bracket. So the expression here becomes minus 1x plus 2x minus 4 plus 3x minus 12 minus 4x and plus 16, it becomes 0. So what is the meaning? What is the significance for the bending moment? The zero bending moment is a point of contrafracture, a point of transition where hogging and sagging occur. This is the change of sign. It was bending upwards and it has changed, now it's bending downwards, or vice versa. It can be hogging to sagging or sagging to hogging. Let's see for the shearing force expression. The range of CA, shearing force, is 1 kilonewton. The reaction at CA is 1 kilonewton, and the range at AB is negative 1 minus R1. It becomes -1 plus 2 equals 1 kilonewton. So the range at dB is -1 plus 2 minus 4 plus 3, it becomes 0 kilonewton. Let's now see the diagram, how it look like. As I said, from 0, the CA range, 2 kilonewton, the bending moment. Then it went back to the range of AD of positive 2 kilonewton meters. So it looks like that. For the shearing force diagram, we had a negative for reaction A, reaction at A or reaction R1. Being negative is the direction that from origin position, it has to move downwards up to 1 kilonewton. Then it has to go back. We had 2 kilonewton here. So one is to bring it to the neutral position, 1 magnitude here, and the second one is for raising from neutral position or from origin. So it becomes 1 kilonewton above the origin line. See the 5th example. Determine the expression for the bending moment and the shearing force distribution for the following simply supported beam. Otherwise, plot the bending moment and shearing force diagrams. For this case, what has changed here is this. Watch here carefully for the directions of this arrow for the force that is acting at this direction. It's not vertically, it's horizontal to the beam, but summing it, where will it go? It will be clockwise. For both, it is clockwise moment. It's the only difference here, making from the previous ones that we have to work to see on how this 6 kilonewton meter force is acting here. Let's work out for the reactions. Taking moments about B, standing at B. Where is B? So B is here. Let's see on how you can compute for reaction A or reaction 1. Taking moment about B gives R1 times 3 plus 6 times 1 is equal to 4 times 2. Six times 1, remember we are at B, and the other one is 2. This one is going downwards. Oh, it's going clockwise, anti-clockwise. This one is going anti-clockwise. If we are here, the beam moves this direction. If it moves this direction, the moment of anti-clockwise is 2 times 4 kilonewton, equating with the 1 times 6, that is clockwise, plus 3 times R1 or RA, because RA goes the same direction with the 6 kilonewton meter. So R1 can be computed that summing the like terms, it becomes 8 minus 6 over 3, making R1 the subject. So R1 is 0.667 kilonewton. So R1 becomes 0.66 kilonewton. Yes. Resolving vertically, it gives that 1 plus R2, R1 plus R2 is equal to 4. The only another thing to note here, the forces acting upwards, R1 and R2, and the forces acting downwards is 4. Is simply 4, and this one is not included because it's the balances, so it cancels this one and this one. So we only regard the 4 for the forces acting downwards and the ones going upwards. So it's 4 comparing or equating to the forces R1 and R2. Yeah. So range at CD, bending moment expression, x at x is equal to R1 times x, and you know what is R1 is 0.667 x. So the range at CD, it is R1 times x minus 4, the force, in bracket x, the minus 1 meter, in bracket gives this expression. So bringing together the like terms, it gives the expression 3.33x plus 4 is a straight line. So this one is, let's see, for shearing forces, range of AC, at AC, you remember that we had the reaction that is 0.667 positive going upward. Range of CD, taking R1, which was going upwards, minus the 4, which is going downwards. So you remain with the downward, which is 3.33 kilonewton. At the range of dB, take R1 minus 4 is equal to 0.66 minus 4 gives you the minus 3.33 kilonewton. So the diagrams now for the bending moment and the shearing force will look like this. Positive is 0.667, and just to go downwards, when it reaches negative 2.66, the mark at the range of CD, then positive, changing the direction, that is 3.33, making 4 in total. Then going back to origin. So for the shearing force, the positive is 0.667 kilonewton, and for the negative is 3.33. Then going to the origin position where we had the reaction here, reaction at B. Another example, this one. Now it's a different type of beam. Determine the expression for the bending moment and the shearing force distributions for the following simply supported beam. Hence, otherwise plot the bending moment and the shearing force. Now let's see on how this one will look like. It's another type of beam. Bending moment range at AC. At AC it is bending moment at AC AC. At AC, it is negative 4x, and the bending moment at CB, it is negative 4x minus 6. You know where 6 is located. Total distance is x minus 2. It gives the expression negative 10x plus 12 is a straight line. Shearing force expression for the range of AC is negative 4 kilonewton, and the range CB is 6 minus 4 minus 6 becomes minus 10. Very quickly, you can go now for the diagrams, how they look like. Now you can see the diagram for the bending moment, the range of AC and the range of CB. Shearing forces start with negative 4 followed by negative 4 going back to origin. Determine the expression for the bending moment and shearing force distribution for the following simply supported beam. Where now you can see the force that we had in the previous question. The total distance here is 4 meters. This one is parallel to the beam, and this one at the hanging point. The range AC at x, so it is negative 2x, a straight line. The range of CB is negative 2x plus 6. Shearing force at AC is negative 2 kilonewton, and the range at CB is negative 2 kilonewton. So negative 2 to negative 2. Let's see how it looks like. Yeah. So negative 2 here, negative 2 there, the shearing force, negative 3 kilonewton meters and negative 3 kilonewton, making 6. That's how this thing will look like. Let's see another type of beam, another type of loading. Determine the expression for the bending moment and shearing force distribution for the following simply supported beams. This beam is a simply supported one. The only difference here is how the load is subjected to the beam. This is a uniform distributed load, 6 kilonewton per each meter. So total load. Now we have to work to determine the total load for the beam acting where at the center. If we take the 6 kilonewton which is acting at each meter, so we have to multiply by total number of meters along the beam. It becomes 42 total load for the beam. By inspection, R1 should be equal to R2. It is equally spaced. The supports are equally spaced. That's why R1 and R2 will be equal. So R1 is equal to R2, but the total amount for this beam is 42 kilonewton. We have to divide equally for the R1 and R2. It becomes 21. So the bending moment expression for this case, being at x, bending moment will be R1 times x, the total distance, minus 6x squared over 2. Mind you, we had 6x times x over 2 because we want to go for the halfway from this one. R1 times x minus 6x, and because we are looking for This first x is for the distance to make this load total load. In order to determine the total load, because we had a load per each meter, then taking 6 multiplying by total distance, which is x, you get now the total load. So outside is the total load. And inside x, total length, divided by 2, you get the load will be acting at the center of the load. So x minus divided by 2, you get the distance to multiply. So that's how it gives the 6 squared over 2. So now such kind of expression will be a parabola. Parabola. It's not a straight, it's no longer a straight line. So shearing force for this case will be at x, shearing force is R1 minus 6x. And so R1, which is 21 minus 6x, it becomes a straight line as well. See how it looks like. So the beam is of this nature. If you plug the numbers, you get such kind of a diagram. It was 21 upwards, 21 downwards. R1 and R2. This is how the beam gives the expression. Okay. Another form. Say it does the same. Determine the bending moment and the shearing force. Here is 5 kilonewton per meter, and the total length is how much? It's 12 meters. As we computed for the first case, that is just to reinforce 5 kilonewton per meter. That means if you multiply by 12 meters, you go to the total load for the beam. It becomes 60 kilonewton. So by inspection here, this beam is equally spaced. So R1 must be equal to R2. This makes that R1 plus R2 is equal to, to 60 kilonewton. So getting one here, it was supposed to be getting here. That means R1 is equal to R2, which is equal to 60 divided by 2, it becomes how much? 30 kilonewton. So R1 is equal to R2, which is equal to 30 kilonewton. Oh. So bending moment expression at x is equal to R1 minus 5x x squared over 2. It becomes 30x minus 2.5 x squared. Also, it gives the parabola. So the shearing force here at x, it is R1 minus 5x. So what is R1 is 30 kilonewton. It is 30 kilonewton minus 5x. Also is a straight line. So the diagrams looks like this. becomes a parabolic shape, and the 30 positive, 30 negative downwards. Another one. Cantilever here. So the bending moment here, it becomes at x is 6 squared over 2. Mind you, this is the, where does this expression comes from? We said 6 kilonewton per meter. And the distance is how much? It's 5 meters. So in expression, this one becomes, first of all, x, a, b, x distance, because now this is equally, simply equally distributed. So we have to multiply by x in order to get the total load. Where now does it act? It is half, or at the middle of this beam. So at the middle, we have to take the x divided by 2. So the distance becomes x over 2 times 6x. It becomes 6x squared over 2. That's why our case is indicated this way. And the negative is for the direction. Shearing force expression comes minus 6x and making a straight line. Because it's a cantilever and is supported on one side, so the bending moment for this case will be at B. Can you see? Then the shearing force will be at 30 downwards from B. Our B is somewhere here. Another example that is, it does the same. Now it's 5. We had 6. Let's see how this one looks like. Again, here is 6 squared over 2, which becomes the bending moment 3x squared, which is a parabola we know, because we have this expression here. So the shearing expression here, it becomes negative 6x. It is a straight line. So simply now can go for the shearing force. The bending moment and shearing force diagram are shown below. Bending moment expression, shearing force expression of negative x, straight line. The bending moment and the shearing force, this does not make sense here. So to come to this expression. So this is how the bending moment will look like, and the shearing force diagram will look like for our case. Thank you for your cooperation in this discussion. See you next time.